In this next subsection, I want to introduce suffix arrays. They're very related to suffix trees, but much simpler, both to understand and, as we will see, to compute. Nevertheless, they capture the essence of what makes the suffix trees magic, and they will eventually solve this problem of constructing suffix trees in a very elegant way by using suffix arrays as an intermediate result. So let's see what suffix arrays are about. One observation that we can make in a suffix tree is if, so one assumption here is that I'm ordering the edges going out of an internal node by the lexicographic order of the first character. So here the dollar is always the smallest in our alphabet that comes first, then A, then B, then N. And the same is true at every node. B comes before N. If I do this and I look at my list of leaves, I notice that the leaves list the suffixes of the text in sorted order. They're sorted lexicographically. Dollar is the smallest, then comes A-ban, then AN, and so on and so forth. Okay, that's a simple observation. But what we'll do now is essentially ignore all this part on the left, throw away the entire tree if you want, and only keep this list of sorted suffixes. That is the suffix array. More specifically, we store an array L, and I tend to think of L to stand for leaves. That's the leaves of the suffix array. And remember okay, let's do the algorithm first. But remember that the leaves actually store a number, not the string really. Right? This would be, I don't know, whatever the last position is, a 9. So these would actually store the starting index of that suffix and not a string, which also means L is just an int array. It's an array of numbers. Okay, much simpler than a tree in terms of how to represent it. What can we still do if we don't have access to the suffix tree, but only to this array of leaf entries, the numbers in the leaves in left to right, well, left to right if you draw the tree in the normal way, top down in my way of drawing it. What can you do if you just have the sorted leaves? It turns out that's definitely enough for string matching, because we can use binary search for a pattern. Suppose we want to find if the text banana ban contains Anna, the Spanish Anna. How would we do this? Well, we do a binary search for Anna where we fill it with dollars in case of doubt. And, well, how would this work? We would probably start comparing here. Anna is smaller than this because the first character where we have a mismatch is the N, and dollar comes before that. So initially we had it's somewhere here. Now, because it's before that, we know it's somewhere here. And then I don't know how the type breaking is implemented. Maybe this is the next to compare. So we compare this with Anna. So here the result was search in the upper half. Here the result is Anna comes after ab. So we go down. And that means we have narrowed down the interval to these two nodes. And maybe here we would compare with this next. And then Anna actually comes after this. And then we're left with this single position. And now what we do is just check if Anna is a prefix of the suffix at this position. And if that is the case, then we have an occurrence of the pattern. And if not, we don't have an occurrence of the pattern. And so with a simple binary search, we can solve the string matching problem. So what we need for this, the complexity of doing string matching with a suffix array is log n. That comes from the binary search. We have to cut the range in half log n times, or roughly log n plus 2 for rounding. And each of these comparisons, whenever I ask, is Anna smaller lexicographically than this text, each of these checks needs actually m text character comparisons, because we have to scan from the left, or in the worst case, m character comparisons, because we have to scan the pattern of the text from the left. That way. All right. So we can search for occurrences in the text. And another little comment that I want to make is you can actually find all occurrences in the text just as easy. There you just do 2 binary searches. And for the second one, you use Anna with, I don't know, another symbol that is bigger than everything in the alphabet. So it's just you search again. In this first binary search, you pretend that the next symbol of the pattern is coming before all the actual symbols. And in the second search, you pretend it's coming after all the symbols in the alphabet. So what you will find is the first position ends, the first search ends here, and the second search ends here. And that gives you a range, and all the leaves in that range, if it's non-empty, start with Anna. So it's even, in a sense, it's much easier with suffix arrays to solve these variations of the problem. Find me the first match, all matches. These are fairly easy to do because you can conveniently find all matches grouped together like this. But that's more of a side remark. So we define the suffix array as this leaf array. So here it is. As I said before, the actual value stored in the suffix tree is not the string, but the starting index. So the suffix array is just this list of numbers. And the rth entry in the suffix array is the starting index of the rth smallest suffix in lexicographic order. Okay, that's the suffix array. Let's see if you digested this. Where's my question? So similar to before, it's a multiple choice. You can take as many answers as you want. And some of these are correct. Not all of these are correct. And I'll give you a minute to digest all these statements. I'll wait for the 25 answers again. I know these questions need a little extra time because it's a lot of text to read. I see 19. We could do a few more. Okay, 24. One more to go, and then I can tell you which ones are the correct answers. There we go. So here are your votes, and as always, let me lock it now. So the first statement says that the suffix array lists the start indices of the leaves in left to right order. Now, left to right, as I said before, if you draw the tree in the normal way and not tilt it to the side like I did. But that's correct. If you order the children of every internal node in the suffix tree so that the edges are sorted as well. You have to do this in a trie. You don't usually insist on this. A tree doesn't have to be ordered in that sense. But for this correspondence to hold, it's necessary. This suffix, well, T starting at LR is the path label in T to the leaf storing R. That's not quite correct. But a slightly different statement is correct. This is the path label to the rth leaf in T in left to right order. The leaf storing R, well, that's the suffix starting at position R. That's a different beast. Okay, these can sometimes be the same, but they are not in general the same. Different way of saying this, TLR, so the suffix of T starting at position L of R, is the rth smallest suffix in lexicographic order. That is correct. That's the same as saying as the first statement if you want. The next one's an interesting one. It's not correct. If more needs, it means strictly more. In terms of the theta class, if you ignore constant factors, then the suffix tree and the suffix array need the same amount of space. The difference is only in the constant factors, but the factors are substantial. So in a sense here, the theta classes are betraying us in this instance. They don't really give us the interesting distinction here. But it's true, the two have the same theta class in terms of space. And the last question, L and T, well, one of them suffices to solve the text indexing problem. That is true because we defined the problem as supporting efficient searches for patterns. You can be, what efficient means, maybe you can be Catholic about this, but I marked it as correct because a running time of log n times m is very efficient compared to the n times m. Log n is much, much smaller than n, so this in practice is very efficient. Okay. If you have more questions about the definition, then please use the Q&A. Other than that, yeah, keep in mind this this definition here, the one that also most people voted for. Think of the suffix array as storing what's the rth smallest in sorted order. I'll later have another picture how to remember these things. We'll come to that. What I want to talk about next is how to construct suffix arrays. It's fine, we can, if we have the suffix tree, then we can just read the leaves from the tree. But I mean, hold on, we wanted to compute the tree and didn't know anything except my statement that there is a magic black box that does it. But we want to dig into this. So relying on suffix trees to construct suffix trees, that sounds like it's not going to work. But we now have a much simpler object. Instead of this complicated tree, we just have a sorted list. And sorting is something we know how to do. So we could just take all the suffixes of t, put them in an array, and send that to your favorite library method for sorting. Use the Java sorting method. That's a handful of lines of code, very easy to do. And it's for small examples not even that bad, but it can be very slow. And the reason is that if this is a general purpose sorting method, it relies on pairwise comparisons. And comparing two strings essentially means comparing them letter by letter. And in the worst case, you have to scan the entire two strings before you find which one's smaller. And well, if they differ, and if so, which one is smaller. Because we're talking about suffixes here, and we always have the end of word marker, they will always differ. They cannot be equal, we know that. But because suffixes are potentially as long as the text, or just slightly shorter, this comparison is very expensive. So we might need n squared log n time in the worst case, and that is a bit slow. Now, what can we do? We can do much better in two ways. The fancy version that we will just start looking at today and finish off tomorrow. But we can also do something that gets us a fairly long way and is much simpler by just exploiting that we're sorting strings and not arbitrary objects. And this is what I want to talk about first. I call this fat pivot radix quicksort. That's a fancy name for a fairly simple idea. You remember a quicksort. Quicksort was essentially taking a pivot element, and then you take your list and partition it into classes that are, well, by comparing with the pivot, you can have elements that are smaller and bigger. Here we do something slightly more refined. We don't split everything into smaller and bigger. We split it into three groups, and we look at just the first character of the pivot. So this first list is all the strings that have a smaller character at the first position than the pivot. B and A are both smaller than S. And the last list is the same thing, but now with the strings that have a letter that's bigger than the first of the pivot. And then the middle list is all the strings that have the same first character as the pivot. And this is all that we do. We never, in this radix quicksort, we never go beyond the first character. We don't do a full comparison until we can decide it, but we allow to keep these equal results for now. And fat pivot just means this is essentially the fat pivot partition. These are all equal to the pivot if you only look at the first character. And the rest is just as in quicksort. You recurse with the same idea, keeping track of which position you have to check next. So the important point here, that's why I grayed the S out. The important point here to remember is in this middle partition, these were all the strings that had the same character as the pivot. That also means they all have the same first character. So we can ignore the first character for now. We know it's equal. They have a common prefix. And we start comparing with the next character. Okay, let's see how this continues. We have this little tiny list. We do the same process with this pivot. So, well, these are obviously in the wrong order. Sorting is hard. Apart from that, this is an easy case because we end with two lists of just a single element, so we don't have to further recurse. Now we split the second list. This is more interesting. We pick the pivot she, and we're looking at the second character now. So there's a couple of strings that have a smaller character than H. there's one string that has a bigger character than h, and there's a couple of strings that have the same character as h. And now look, what happens here is in this list, well, we as human, we see these all have the same second character, but the algorithm doesn't know that for now. It only knows that they all have a character that's smaller than h, but we still have to compare this. So we're still looking at the second character in this string, in this sublist. Whereas here, this is the partition that had the same character as the pivot. So here we know these are all h, so we can advance to the next character in this list. And again, in the last list, something funny happens. This happens to be the same characters, the same strings, but the algorithm doesn't know it. It uses the next pivot and finds that the first characters are equal, so it only produces the equal partition, but that's where it stops. Then the next round of recursive calls splits the non-singleton lists further up. So we have a pivot here, and it turns out, as we've seen, all of these have the same second character. So they all just move to the next position. There's no splitting going on. And for this list, we have one that's bigger, and the others move on to the next. I think I made a mistake. This should be done. We're looking at the L, and we're looking at nothing here. So sorry, I goofed in this example. This should have moved on. And in the last list, we again find only equals, so we move on to the next position. And here we do this one more time. We partition around this. There's a couple of strings that have a smaller third character, and there's some that have the same. So here we move on to the next position. And here I just I should have omitted this this one step, but now comes the right version. So we move past the last character in the pivot, really. So this is, we fill that with dollars in that case. And well, again, this should have been here. I don't know, something went wrong on the slides, I think. And with these, I'll fix the slides for that. But so here we scanned past the entire strings in both cases. That's where we notice that the two are actually equal. But we have to scan the entire strings for that. And one more here. So here we have to continue with the pivot. Again, we find these are all the same, so we move to the next position in the string. Same happens for these. And here we split off the two equal ones, go here, and then that's a bigger one. It's a singleton list, so we don't have to further partition. And well, in this case, we split one string off, and then these two are equal, but the algorithm doesn't know that yet. It has to continue scanning through the entire string. And only at the very end, it will notice that these two are the same. So what we did is quicksort, but we partition only on the dth character. And initially d is 0, but then it gets bigger in the middle partition. We create 3 segments, the strings that are smaller, equal, or larger in this dth symbol, and we recurse, where in the middle recursion call we increment d. So in code, this algorithm looks very, very similar to quicksort and is very easy to code. An important observation here is we never compare equal prefixes twice. If two strings have a common prefix, we will compare that. We will have to find out that they have they have this shared prefix, but we never scan them several times. And this is what made the direct call to a string method slow. Someone's saying that the video stopped. Seems fine on my side, so I'll continue. Because we never compare the same, well, the other way around. For a standard sorting method, we repeatedly compare strings, and it could happen that we compare the same shared prefix many times, and we have to scan over this many times. Okay, so if your video has stopped, refresh, but if you can hear this, then it hasn't stopped, so it's not very useful that I'm saying this. What we can say about this fat pivot radix quicksort is that for a certain model of strings, if the strings are random, then we only need n log n time instead of the n squared log n that a standard sorting method might have in the worst case. It's very simple to code, and well, this expectation is about the choice of pivots, but it works for all texts. So if you choose random pivots, you will usually see behavior in this realm. It's very simple to code. It's very efficient for sorting strings, even if they're not suffixes. And we can also apply it to find the suffix array in n log n time. That's already quite good because we started with something quadratic. Reducing that to n log n gets you most of the way. Because it's so easy to code, it might actually be a method of choice if it's not a performance critical application. But still, sometimes this is still a bit too slow, and from a theoretical perspective, it's more time than we need, because we can actually do linear time, and this is what we'll look at in the next subsection.